We are here today because the industry's standard approach to furnace productivity has hit a mathematical wall. For decades, we have relied on the RAFT, the adiabatic flame temperature, as our primary compass. But as we push into modern high PCI operation, that compass is spinning wildly. So today I am going to decode what we call the Bosch gas code. So look at the title slide. You see those emerald laminar streamlines on the right contrasting with chaotic, turbulent orange plums on the left. That is the visual representation of our challenge. By the end of this session, you will gain three critical deliverables. First, a clear understanding of why traditional indices fail modern furnaces. Second, the introduction of HMR Index as a superior predictor of yield. And third, a roadmap to achieving stable, stable, consistent, record breaking daily output of over 6,500 ton while slashing the operational cost. So let's dive into the data. To understand where we are going, we must first confront the failure of our current metrics. So our next slide is exactly addressing the big picture, that is a crisis of correlation. So as we are currently facing an operational crisis distinguished as a normal variance. So look at the table on the left of the slide. So we have historically expected a linear positive correlation between RAFT and productivity, but the actually whatever the R square value is coming, that the R square value in our high PCI furnace is effectively zero. So it is just a scattered mess. So the graphic on the right illustrates the beautifully. See the blue laminar flow hitting a vertical orange wall of failed metrics, resulting in what we call turbulent data scatter. So this gap between our theoretical hit calculations and our actual yield is costing us hundred of tons in daily output. We have been trying to drive a modern machine with a map from 40 years ago. When the math doesn't match the metal, the furnace rejects the hit and the plant loses money. We need a new index that actually correlate with the physics of the raceway. This is not just a theory, we have backed this up with a massive data landscape from some of the world's largest furnaces. So coming to our data landscape, just now, yes, now I have changed the slides. Uh, so here you can see our intelligence didn't come from a small scale lab. It come from largest classroom on earth. So notice the interconnected nodes, which represent aggregated high resolution Bosch gas telemetry from global mega furnaces, specifically Visco BF1, CSC BF2, 3 and 4, and we are looking at millions of continuous operational minutes where we stripped out shutdown noise to isolate true raceway physics. So the table shows this, um, which have a inner volume of shows this blast furnace having inner volume of range of 2200 to over 3400 meter cube. So all running high PCI and oxygen practices. We have mm, married the black box machine data with the forensic level telemetry to find the hidden pattern. So by analyzing this global leaders, we have moved beyond site specific uh, to find a universal law of blast furnace productivity. So we are not just guessing anymore, we are operating on the back of massive validated time series data. So from this global data set, one specific trend emerged that changed everything we thought we knew about the heat. And that is about the top insight number one, the HMR productivity curve. So this is what is all about our slide. The most surprising trend we uncovered in the linear relationship between production and what we have termed the HMR index. So follow this neon green arc on the screen. Notice how production increases linearly as the HMR index decreases. The data table in the lower left is undeniable. At an HMR of 110, we see a production of roughly 4,200 tons per day. But as we lower that index to 30, it skyrocket to approximately 6,500 tons, maintaining a consistent R square of 0.73. This tells us that efficiency dictates yield. When we make better use of heat and reductant, the furnace inherently reward us with higher output. This is the wow finding. Lower heat to reductant ratio, when managed correctly, actually drive higher productivity. So it's a counterintuitive shift from the hotter is better mentally. But the physics of the Bosch gas flow doesn't lie. But a 0.73 correlation was not enough for us. We needed to find the hidden stratifier to reach absolute precision. So top insight 2, which is nothing but oxygen. And as you can see, the hidden stratifier, if an R square of 0.73 was the foundation, oxygen management is the secret architect. So look at the top graph on the right, which looks like a chaotic magenta cloud. When we filter that chaos by oxygen enrichment layer, as seen in the bottom plot, parallel perfection emerges. The table on the left shows that while the mixed data set sits at 0.73, stratifying by oxygen levels, specifically the 0% to 2.5% range, jump our mathematical correlation above 0.91. This is a massive forensic breakthrough. It proves that the oxygen is not just a fuel booster, it's a structural stabilizer for the Bosch gas. So by understanding these parallel layers, we can predict furnace behavior with a near telepathic accuracy. The operational impact is clear. If you are not controlling for your O2 enrichment layer, you are flying blind. We have moved from a scatter shot approach to parallel perfection in our yield forecasting. This mathematical stability is only possible if we stop trying to brute force the furnace and start optimizing it. So coming to our next slide about our top insight 3, that is brute force versus optimization. We have to stop pushing excess gas volume which destroy permeability. On the left, the tall orange bar represents the brute force method, that is high specific heat and reductant consumption that lead to a choked furnace and a yield capped under 5,000 tons. Conversely, the emerald bar on the right represents the optimized HMR approach. So notice the magnifying glass icon. It highlights the transition from turbulent to laminar flow. So by lowering the specific consumption of heat and reductant per ton, we achieve a laminar permeability state, which is the absolute prerequisite for the peak production exceeding 6,500 ton. So saving on fuel by over-injecting is actually costing us millions in lost yield. The so-called hot furnaces is often just a choke furnaces. Real productivity comes from a lean, laminar gas stream that allow the ore to descend smoothly. To master this laminar flow, we apply PSPP framework to the furnace raceway. And this is what about deep dive number one and the PSPP analysis, which is all about deep dive one. So let's apply the process, structure, property, performance framework to the raceway. This glowing schematic shows the transformation path. Node 1, the process is your win rate and PCI, the two-year injection. This dictate node 2, the structure, which is your Bosh gas composition, that mix of hydrogen, CO and nitrogens shown in those vibrant orange and magnetous fields. This structure determines node 3, the property, which is a sensible heat or the H by R ratio. If the H by R is wrong, viscosity and permeability, the forged amber zones will suffer. Finally, this leads to node 4, the performance your daily hot metal yield shown in crucible emerald. Damage start at the gas structure level, not at the tap hole. When we change the process inputs, we are fundamentally altering the chemical architecture of the furnace. If that architecture is unstable, the performance will inevitably collapse, regardless of how much wind you blow. So when we master this structure, we see operational stability manifest mathematically over time. So coming to our next slide, which is on deep dive number 2, the evolution of stability. And as you can see, this slide is mathematically visible. So the four scattered plots on the right look at the progression from the top normal state to the bottom. So lock state over an 18-month period. We watched our correlation R square move from 0.84 to a staggering 0.98 in early 2007. The table on the left break this down as we move from normal to stable to highly stable and finally to locked. Our yield become entirely predictable. Strictly controlling wind rate and oxygen management is what drives this HMR to production correlation to near absolute predictability. So when your data looks like that bottom line, a sharp tight blue diagonal, your furnace is in a state of laminar stability. This level of control allow you to push the furnace to its physical limits without the fear of sudden slip or hanging event. It's the difference between gambling and engineering. So if we do not have this stability, we must ask the five whys to find the root of our ill caps. So coming to our next slide, which is about the root cause, the five whys of the heat rejection. So why is our yield capped? So because the furnace is rejecting heat. Why is it rejecting heat? Because of poor gas solid contact pattern. Why is the contact poor? Because of severe permeability issue. Why is the permeability poor? Because the gas volume pattern is very high. And here is the root cause at the bottom of the stairs. The H and R inputs are not scaled to the HMR index. We have been forcing excessive heat through the tuyer, which which create a problem for the optimum contact pattern, which is also needed for to process the ore. So high gas volumes are not a sign of power; they are often a sign of inefficiency. So the root cause of the almost every yield bottleneck we have analyzed is an imbalance in the heat to reductant scaling. We are trying to process too much gas and not enough ore. So however, as we optimize HMR, we must be careful not to cross a dangerous thermal boundary. So now our next slide, which is about the safe zone, uh, safe zone versus danger zone. The raft ceiling, optimizing HMR, has a physical ceiling and we must respect it. So look at the raft temperature on the y-axis that we have shown. The green zone is safe under 2000 rather 100 degrees centigrade. The yellow optimum zone sits between 2100 2300. But look at that jagged white line at the top. The moment you exceed a 2300 raft, you invite a catastrophic instability, as is known to everyone. So the table on the left is your operating map. We have already shown all this data where HMR of 39.4. If your raft crosses that 1300 mark threshold, so you enter the failure zone. So mathematical solution that looks good on the spreadsheet but exceed these thermal limits will destroy your refractory and lead to a slag instability. So staying in the emerald zone, avoid the coral emerald zone. So avoid the coral zone. We want a highly productive furnace, not a melted one. So maintaining this balance is the hallmark of the senior engineers or the managers. So to stay in that safe zone while maximizing yield, we must focus on our primary level. So coming to our correlation matrix. So I think I could not able to shift timely this slide. So this is all about the correlation of the so as you can see that the sensible hit is exquisitely sensitive to two-year practices, but one variable stands above the rest. In this web, HMR is the central sun with the wind rate, PCI oxygen orbiting. Uh, so as the table shows that wind rate has a direct and high impact on the Bosch gas volume. PCI injection directly drive the reductant value, but notice now row number 4, that is wind rate, and wind rate is the primary driver for daily yield. So it acts as a dominant lever for the scaling productivity without destroying permeability, provided it's balanced with the right HMR. So think of it as a coupled reaction. You cannot move one without affecting. And by focusing on the wind rate, our primary scaling tool, which is our primary scaling tool, so we can maintain the delicate chemistry of the Bosch gas while pushing the more pushing for more tons, we can say. So it is about a precision, it is not about a volume. So let's look at a real world case. Yesterday we are shifting the wind while holding HMR constant paid off, and which is about a case study. So here is a practical comparison in case A. You can see we have a medium in rate of 4,400 and producing 6,000 and with an HMR of 39.4. Now look at case B. We increase the wind to 4,700 while holding that HMR constant 39.4 as it's shown in the slide, row number 2. So the what is the result? So we gain 362 additional tons daily, reaching 6362 ton hot metal. So crucially, notice the Bosch gas reading. It actually decreased slightly from 65.43 to 64.95 kilomole. So this is the magic of HMR index. By shifting to a high wind rate while maintaining the thermal balance, we avoid specific fuel spikes and efficiency loss. So we are producing more metal with a less specific gas. This is how you unlock hidden capacity in your existing asset without spending a dime on capital upgrades. So if we push this logic to its extreme, what is the ultimate potential of the furnace? So which is all about the predictive breakthrough. the 6,800 ton. So if we look into this slide, this is basically a horizon modeling extreme efficiency forecast, a future that was once thought impossible, that is 6,800 ton daily. So to reach this predictive breakthrough, we have to aggressively minimize the HMR index to 20.4 through balance input. As shown in the table, this requires a RAFT in the safe zone of 2087 to 2145 and a record low fuel rate of approximately 304. So this is not just a dream, it's a mathematical destination. So look at the slope of that line. It's a steep, it's stable, and it's emerald green. So reaching a 6,800 ton requires us to shed the old, hot and heavy fuel practices and embrace an ultra efficient low HMR profile. So this is the new frontier of iron making. We are moving from a world of good enough to a world of predictive telemetry. So beyond the turn, the most compelling reason to make this shift is the bottom line, and which is all about the